Okay, well, welcome back to the Chapter 6 initial discussion. We're dealing with the transportation problem. And first thing I'm doing is giving you a practice problem number 1 for transportation. I've got 3 questions to give you, and I'm going to show you how to do this both graphically and in parts A and B to develop a linear programming model, and then to develop the optimal distribution plan and cost using Excel. So these are the data that we're given. For part C, again, we would use Excel. These are the shipping costs per source and destination that we're giving. So this company, Training Transport, moving goods from 3 factories, source A, to 3 distribution centers, destination X, the destinations X, Y, and Z. Information is given below in terms of supply at the source, demand at the destination, the costs of shipping from a given source to a given destination. So when we set this up graphically, I will take you back to the pages where the instructions are given. So I tell you, when they're doing the network model setup, we draw those origin nodes on the left side, destination nodes on the right side, and the arcs connecting in the middle. So let me take you back to how that should look. So we draw our origins, A, B, and C, on the left side, our destinations over here on the right side. We draw the availability of, the supply, 200, 100, 150, on this side, and I guess I cut this off when I captured the screen image, mea culpa. We also want to show the demand over here on X, Y, and Z, and therefore we should have 50, 125, 125. I'm not going to make that edit right now. We should have 50, 125, 125. That's how we would draw the network representation of this problem. That would be the answer to part A. Let's look at part B, develop a linear programming model that can determine a plan that will minimize total distribution costs. So key right away is that it's a min. So the LP expression given here, but let us take you through first the instructions. I told you previously that you're going to want to have this available to you. Maybe you print it, have it somewhere you can reference it. So each arc has a unique, it becomes a unique decision variable, and each of those is identified as an X with a subscript that shows the source and destination. Coefficient of each is the transportation cost. So let's see what that looks like. So each of these lines is a decision variable. Remembering we were just told that this is a min, so we look at each of these lines and we say that the cost is the coefficient for each that decision variable. So the cost for A to X is 3. So we say that that's a decision variable. We have to decide how many we're going to ship from A to X at a cost of 3. So that's given as 3x subscript A sub x, AX, A to X. Then we have 2 here. So that would be, for our coefficient form, the coefficient from A to Y, 2x sub AY. And we have 5 here from A to Z. So that forms our coefficient of that decision variable, 5x sub AZ. That repeats itself for 9, 10, 6, which is out here, 5, 6, and 4. So in this case, there are 9 arcs or 9 lines, given that there are 9 potential paths from sources to destination. And there are 9 decision variables. Remember what I told you previously, Chapter 2, how many decision variables can we solve simultaneously using graphical methods? Only 2. Well, we have 9. That's why we need to use computer solutions. Okay, now let's define the constraints. So, how did I tell you to define the constraints? There are supply constraints and demand constraints. The number of those constraints is equal to the number of nodes. Supply constraints. Each arc is defined as X with the subscript, and the sum of those variables must be less than the capacity. On the demand side, the sum of the variables must be less than the total demand. So what does this look like? So we have 3 nodes on the supply side, 3 nodes on the demand side. That means we have 6 constraints. If you notice what I've written here, 1, 2, 3, 4, 5, 6. So each of those constraints is associated with the node. And each of the constraints defined for that node is the path from A to X, A to Y, A to Z. So X of AX, X of AY, X of AZ must be less than or equal to the supply available at that supply node. Node B has the same, mea culpa, I left a decision variable, or a constraint variable out here. That would be X sub BZ. Now, I had made some changes to a previous example, and that's why I have some of the computer writing on top of this. And then node C are these three arcs here, XCX, XCY, XCZ, must be less than or equal to 150. The demand constraints are given the same way of each of those arcs, and they sum to equal, not be less than or equal to, but equal to the demand, which, as I noted before, would be 50, 125, 125. So we have three demand constraints. And finally, we have the non-negativity constraints. Won't hold it against you if you don't identify that, but those are something to say we can't have negative values for these constraints. All right, so how do we do this? We're going to solve part C, describe the optimal distribution plan and total distribution cost. Let's look at how that would look using Excel. Let me find the Excel version. Now, I told you here to find the Chapter 6 transportation template file. Download that from Canvas. We're going to work using that. You're going to have to do this for the Chapter 6 test as well. So here we are. I pulled the template down. So we have origins A, B, and C. We have destinations X, Y, and Z. We have supply of what is, let's refresh my memory, supply 200, 100, 150. So let's go back here, 200, 100, 150. We have demand of 50, 125, 125, 50, 120, 125, 125, and the costs associated with each of these. 3, 2, and 5. Let's go over here. 3, 2, and 5. 9, 10, and 6. 9, 10, and 6. And lastly, from C to these, from C source to the others, 5, 6, and 4. 5, 6, and 4. Okay, now we're ready to run cells for the students to fill in blue. Excel will solve the rest of them. Let's run solver. This has already been set up in the template. This is a min function. Makes sense. Let's solve. Our minimum costs here is $900. So when we answer the question, total distribution cost, it's $900. What's the optimal distribution plan? Well, this tells us that to satisfy the demand of 50 at destination X, that those 50 will come from source A. To satisfy the demand of 125 at Y, they will also come from source A. And to satisfy the demand of 125 at Z, that will come entirely from node C. Nothing will come from node B. They're not going to ship anything at all. That is how we can identify the least cost, the min cost, of transporting products based on supplies and demands and knowing the transportation costs between those given nodes. This is simply a 3x3. This can be configured to be a 2x6. It can be a 4x4. It can be a variety of configurations, even using Excel. Again, when you have the higher order software solutions like LlamaSoft, you can do a whole lot more, but this gives you the basics. So that's the first part of Chapter 6, Transportation Network Problem. That's all we're going to work on today. Next week, we'll work on other types of problems, assignments, transshipment, shortest route, and maximal flow problems. Okay, that's the end of week 5. Thank you very much, and I'll talk to you and see you next week. Bye-bye.